Okay, as is customary, let me quickly go through the same old drawing and a few common expressions. This is a filter output yn, dn plus minus error en. We had r as, we know what is the xn vector. I am not going to all those definitions. R was T D T transpose, okay. Delta n was W n minus W opt. W opt is R inverse P, we know. K n was covariance matrix of this. Why covariance? Because actually in the steady state delta n test limit is 0. So, in the steady state whether it is correlation matrix or covariance matrix both are same because mean is 0. Then we had defined delta prime n as T transpose delta n, and correlation matrix of this was K prime n. This is our dictionary. Sorry, delta prime n to delta prime transpose n. Okay, and this is nothing but T transpose, sorry, K n T. We also define x prime n as T transpose x n and E of x prime n x prime transpose n, that was D. D consists of the positive real eigenvalues. Okay. Then we are finding out epsilon square n, which is E of E square n. This has two components. One is that epsilon square mean, which you get when you have optimal weights, but since in the steepest descent we did not put the actual optimal weights, but we approximated R and P by some very weird estimates, wild estimates. What we get, what we find is that W n dances around the optimal weight. As a result, E n is not exactly, even in the station, not exactly the optimal error E o n, and therefore, its variance is having an extra component, that component was this. Therefore, we have to see how this quantity behaves in the steady state. Lambdas are bounded, no eigenvalue will take a infinite value, because matrix elements are bounded. Okay, but how this guy behaves in the steady state, how to keep this as n tends to infinity, how this quantity can be kept under check, under some bound as n tends to infinity, so that using some parameter we can control the bound and keep this extra component within a limit. This is called excess mean square error, epsilon square excess, by the way, excess mean square error. Okay. This quantity we want to keep controlled, it should not grow as n tends to infinity. But you see, this has a recursive phenomenon. We have seen that matrix K prime n is recursively built up from its past value. So, there is a recursion, that by recursive way it can grow also, which will be dangerous, because its value will then tend to shoot up to infinity, because we have seen that K prime n matrix has a recursive way of degeneration. We obtain the recursive relation of K prime, obtaining K prime n plus 1 from K prime n and some other values. So, that recursion has this possibility of what, that that K prime n can go on building itself up in a regenerative manner, positive feedback, regenerative manner. Okay. So, you have to see that such thing does not really take place. We have to do things, appropriate things, so that this is kept under check, under some bound as n tends to infinity. That is the whole analysis. For that, we obtain that recursive equation for K prime n. For your convenience, I am just rewriting here again. K prime n plus 1, this is the recursion, was K prime n. This is a slide from the previous day, K prime n minus mu d into K prime n plus K prime n d and plus 2 mu square d K prime n d. D consists of the what? D came from the eigenvalues of R matrix, mu square d trace d K prime n and these things. Okay. Then here we will come to this later. Then here, if you take the, I told you that we are not interested in the entire matrix, we are only interested in the diagonal elements, because the diagonal elements only matter in the excess mean square error. So, you take the ith diagonal entry, ith element of this is ith element here minus mu times, there are two matrices, diagonal times k prime and k prime times the same diagonal. We saw that time that diagonal ith diagonal entry in either case will be same, lambda I times k prime I n. So, twice that minus twice mu lambda I k I prime n, okay, plus 2 mu square and this again k prime n d, lambda 0 times first column, lambda 1 times second column dot dot dot, and then lambda 0 times first row, lambda 1 times second row dot dot dot. So, ith row, ith column, that time I have lambda I square only. So, lambda I square is coming 2 mu square lambda I square, same k I prime n, okay. And then here next one mu square, this is a scalar quantity trace. So, ith diagonal entry of this diagonal matrix D, which is lambda I times this trace, and trace is what? This is the diagonal matrix multiplying this and then taking the trace. Diagonal matrix means first row times lambda 0, second row times lambda 1 dot dot dot. So, that means lambda j times k prime j j. Do not use I, previous or the other day I erroneously use the same index I, because I was also figuring out I is constant. So, it is better to use j or r or k or l or anything like that. Okay. That was a small mistake which skip my attention. So, this thing and plus this, and so this quantity k I prime n, if you take common you get 1 minus 2 mu lambda I plus 2 mu square lambda square. This quantity I am calling rho I, this quantity I am calling rho I. So, rho I times k I prime n plus this plus this. From here we built up. What I will do now, these diagonal entries I will put them in a vector form. That is what I was doing towards the end, and I was just hurried. So, I thought that I would again start from there, because that time I was really hurrying, because they gave me a signal to wind up. Okay, so, if I put them in a vector form, what I get? So, that means I am defining this vector, this is a lowercase k, k prime n, it will consist of capital K, that matrix 0 0th element, first diagonal element dot dot dot, nth diagonal element. I am putting them just in a vector form. Okay. Here I had a recursive equation in terms of ith element, and now I can be 0, I can be 1, I can be 2 dot dot dot, I am putting them in a vector form. In that case, if I collect all the vectors from here, all the elements here from the, generate the vector here. Here also rho I times k I prime n. So, what happens? K prime n plus 1, are you following me? This is k I can be 0, 1, 2, I am putting in a vector form. That is equal to what? Rho 0 is another vector, rho 0 times k prime 0 0 n, rho 1 times k prime 1 1 n dot dot dot. That you can write as a diagonal matrix. You can call this matrix P 0 0 times the same vector, is not it? Rho 0 times k prime 0 0 n, rho 1 times k prime 1 1 n, like that. See, right like that, k rho 0 times k prime 0 0 n, rho 1 times k prime 1 like that. Okay. Plus, look at this quantity mu square lambda I. So, for I equal to 0, this quantity is a scalar quantity, trace, constant. So, this constant mu square. So, we have a very simple thing, lambda 0 for I equal to 0, lambda 1. So, it will be a lambda vector only. I define a vector lambda vector like this, lambda putting all the eigenvalues in a vector form, lambda 0, lambda 1 dot 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 lambda n. So, I have got lambda 0, lambda 1, lambda 2, lambda n, one vector will come up, is not it, multiplied by a scalar mu square and another scalar. And this scalar mu square lambda vector from here, and then this scalar element. This scalar element can I write like this, lambda transpose after look at this, lambda 0 times 0th, lambda 1 times first diagonal entry, lambda 2 times second diagonal entry, is not it? So, diagonal entries in a vector form and then lambda 0, lambda 1, lambda 2 in a row vector, row into column, then you get this. Okay. And once you have that, you can club now these two together. And last one is again very simple, last one is mu square epsilon square mean, which is scalar, lambda 0 for I equal to 0, lambda 1 for I equal to dot dot, so lambda vector. Okay. So, k prime n, I can take p plus k prime n, k prime n you take common one diagonal matrix and lambda column vector times row vector, so it is a matrix, actually it is a rank 1 matrix times the scalar mu square, together is a matrix, that times k prime n plus. Now, those who are from electrical background, I do not know how much control theory they have studied, but they should be pretty familiar with this discrete time state space equations. But students who are coming from our department electronics and all, they may not be. So, for general interest, I will give some produce some general results now, which may be known to that segment of this audience which comes from electrical background, because they do extensively this system theory, or I hope so. I do not know what exactly they do though. Okay. These are discrete, you see this matrix is known, P is known to us, P came from this and rho came from what? Rho depends on mu and lambdas, all mu's lambdas are suppose known to us. So, P is known to us, mu is known to us, lambda vector known to us, P f is a known matrix. So, it is nothing but this is equal to f into k prime n plus this. Can you please see that f is also a real symmetric matrix, the Hermitian matrix here? F consists of what? A diagonal matrix plus lambda lambda transpose. I told you any time you have this kind of form lambda into lambda transpose, that is a symmetric matrix. I j element is given by lambda I lambda j, j ith element lambda j lambda I, but their product is same. In any case, if you take this matrix, take its transpose, you get it back. If you take it this and take the transpose means transpose of P diagonal matrix, you get it back. A transpose of this part lambda lambda transpose, you will get back lambda lambda transpose, isn't it? So, F is a symmetric matrix, real symmetric matrix, I call it real Hermitian matrix. Okay. Now, suppose I give some other results now. Suppose you have, so this is a departure, okay, I am trying to get into something else. So, do not get confused with the notation, this x here is not the x we are dealing with earlier, the general result. Suppose you have got an equation like this, or say x n, or maybe okay, x start with x n plus 1 plus some scalar k times some vector u, u is a constant. Okay. A is given to be, it is a real matrix, real, so it is a Hermitian matrix. These are all real valued quantities. A is a symmetric matrix means A is a real Hermitian matrix, which means A can be written as some T d T transpose, where T T transpose, this T and previous T are different. This is a separate thing I am doing altogether to prove some results. Do not think this T has got anything to do with the previous T, which came from diagonalizing this correlation matrix R. This is a different result, nothing to do with our previous derivation. Okay. This T transpose T is I, that is the unitary matrix, very standard result, because this is A is Hermitian, so it can always be written like that, we have seen earlier. Okay. Now, two things you see, what is a to the power n, that is a dot 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 n times, that is the meaning of a to the power n. What will that be? T d T transpose T d T transpose T d T transpose, like that. Always these two will cancel, like that. Okay. Finally, a d and T transpose will come. Can you see? So, it will be T d to the power n T transpose. And what is d to the power n? D is a diagonal matrix. D is a diagonal matrix. Suppose D is lambda 0, again this lambda is nothing to, is not the same lambda which we are dealing with earlier. It is a local context here, lambda 0, lambda 1, say lambda n. So, d to the power n means all eigenvalues, d into d means what? Lambda 0 square, lambda 1 square, dot dot dot, lambda n square. So, d to the power n means just you square up the, you just raise each eigenvalue to the nth power. Okay. All right. Therefore, if it is that each eigenvalue of this matrix A, suppose by some hook or crook, I make sure that its value magnitude, eigenvalues are real here, isn't it? A may not be positive definite, I am not assuming it is positive definite, I am not assuming too much, just Hermitian is fine, but as long as it is Hermitian, eigenvalues also are real. Therefore, their magnitude suppose lies within 1, that is their value lies between 1 to minus 1, less than 1, greater than minus 1. If that be, then when you raise them to power n, its value becomes still less, and as n tends to infinity, the value approaches 0. So, this matrix will approach a 0 matrix as n tends to infinity, because d to the power n, all the it will become a all 0 matrix. Okay. This is very common in control theory, you know, these are very, I mean, this bread and butter there actually, these things in system theory and all. You understand this? This is one result. Okay. Another result is, suppose I have got this quantity identity matrix plus A plus A square dot 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 dot. There is A square means A into A, another matrix, A into another matrix, and you are adding. There is no guarantee that it will be converging to a matrix of finite elements. That question is open. I am still writing it dot dot dot. It may diverge, it may converge. I do not know. Okay. But this I can always write as A is T d T transpose. A square is T d square T transpose. This is T d to the power n T transpose. I is T into T transpose. So, I can write like this T into I into T transpose. So, I can write like this I, this T transpose I take on this side, D, I am forgetting the underscores, they are there. Huh? Okay. Now, these are all diagonal matrices. So, that means you have got a thing like this T and a diagonal matrix where ith element will be what? Ith element will be, this is 0 here, 1 plus lambda I okay. If lambda I less than 1, if and only if, then only this will be finite 1 by 1 minus lambda I, isn't it? Then only this matrix will be, this summation will be convergent. Then convergent to where? If this is so, this convergent. These are necessary and sufficient condition. If and only if each eigenvalue has magnitude less than 1, then this will happen, because you see all diagonal entries will be 1 by 1 minus lambda something. Okay. Lambdas are finite and therefore, you get finite numbers. And so, this is convergent only if this happens, fine. In that case, what is this matrix? This matrix is 1 by 1 minus lambda 0, 1 by 1 minus lambda 1 dot 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 1 by 1 minus lambda n, right, into T transpose 0 0, isn't it? So, I can always write as T I minus D inverse T transpose. Can I write? What is I minus D? Diagonal matrix 1 minus lambda 0, 1 minus lambda 1, 1 minus lambda 2 dot dot dot. Those are the diagonal entries. Now, you take inverse. So, they become 1 by 1 by 1 by. Okay. And this again you can write T transpose is same as T inverse. So, you can as well think this to be inverse. So, you can do this way T transpose, this T I can write like T transpose inverse, because T transpose is T inverse, this inverse, and this T transpose I can always think of T inverse. You take these two first, A inverse B inverse means B A inverse, isn't it. So, T will come first. Actually, if you are conversant with matrix theory, I can just write this and straight away write the last expression. Oh, these are silly things actually.
Invert, the last elements will come.
Huh?
Last elements will come first.
These two I am taking, na?
If you take 3 together.
That is okay, but I am going step by step. But I do not know how prepared people are, so I am going step by step. Okay. So, here this is I minus this inverse is T into I minus D whole inverse, and again these two B inverse means A B inverse. So, T transpose will go here, and then what happens, T within bracket I minus D T transpose, T into T transpose is I, and T D T transpose is A. So, this becomes I minus A inverse. Is very much like what you have in normal scalar thing, na, 1 by say 1 minus k inverse, 1 by 1 minus k is 1 plus k square plus dot 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 if mod k is less than 1. Here instead of A cannot be less than 1, is a matrix. We say that highest eigenvalue, and I am assuming some structure here, I am assuming A to be symmetric, that is Hermitian, all those things, okay. And then I am saying if all the eigenvalues are less than 1 in magnitude, this will happen. This result does not require, by the way, that A should be, for our case is fine, but this result does not require that A should be Hermitian, because this is I use the fact this is Hermitian, and therefore, I could write A in this kind of form and do all these things, to my advantage. But even when A is not Hermitian, this question of T D transpose and all this does not arise. Even then, this will work out. I minus A inverse will be I plus A square, provided the norm, you have to define something called norm of a matrix. Norm of the matrix is less than 1. One norm of the matrix is called the spectral radius. Spectral radius is the eigenvalue of the highest magnitude. Matrix A may not be diagonal eligible, may not be of this form, but it has some eigenvalues. The eigenvalue which has the highest magnitude is called the spectral radius of the matrix. That works as a norm of the matrix. Now, norm and all this we will learn little later in this course only from me. The spectral radius, it satisfies the norm properties. So, that is working here actually, because all the eigenvalues are less than 1 means what? Spectral radius is less than 1. Anyway, this is what it is. Okay. So, these two I will use here now. I come back to our business. What was our equation? This is our equation. K prime n plus 1 is f into k prime n plus this. Okay. Now, k prime n, if let us see, you again replace by the corresponding recursion. What is the corresponding recursion? This will be f into k prime n minus 1 plus mu square epsilon square mean lambda, and go on doing it. You go on doing it. Again replace this. So, you can see what will obtain is what will happen? F into k prime n, then f square k prime n minus 1, and f into this term. This mu square epsilon square mean lambda, that is common. That is there, f times that is there, next time f square of that will come up. This will give rise to final, if you go to n equal to 0, go back to see from n to n minus 1 to n minus 2, that is how I am going back, okay, backward recursion. And finally, if I stop at n equal to 0, you will see we will have this. Take a minute of yours and see that you will obtain this. It will be f to the power n or n plus 1, n plus 1. and this will be I, the mu square epsilon mean, that will be there already here, mu square epsilon mean and lambda. Just look at the expressions. F into k prime n, you are writing as f into k prime n minus 1, that you are further writing as k prime n minus 1, you are further writing as f into k prime n minus 2, so and so. So, finally, k prime 0 into f into f into f into f types. And what is the other term? This is one term free of f, then one term f into this, then another term f into whatever comes out of this. There again another f is there, so f square. That is why a I a f square, it will be like this. Okay. Now, instead of k prime n plus 1, let me come back to the convention, k prime n, which is f to the power n, k prime 0, instead of n plus 1, I am now taking n. Okay. F is, please see this, I told you F is a real symmetric matrix here. So, all my previous results can work out. If the eigenvalues of F, after all F comes from P and lambda, lambda are the eigenvalues of R matrix, together is a new matrix that has a new set of eigenvalues, say lambda prime, lambda 0 prime, lambda 1 prime, dot dot dot. If those eigenvalues, if you adjust, so that those eigenvalues are having magnitude less than 1, then obviously f to the power n as n tends to infinity becomes 0. So, this part time dependent, I am bothered about only the time dependent part, it should not grow. So, I can make it die down to 0 if I make sure that the eigenvalues of f are, in general the norm of f is less than 1, but in this case I talk directly in terms of the eigenvalues, where f is symmetric, real symmetric matrix, the real Hermitian matrix. If the eigenvalues of f, that is lambda 0 prime, lambda 1 prime, lambda 2 prime, dot dot dot, if all of them are kept within 1 in magnitude, then as n tends to infinity, f to the power n will tend to 0, a 0 matrix that we have seen in the previous, just a little while back, which will make sure that this quantity will not grow. K prime n as n tends to infinity will converge on something constant. This, on the other hand, if the eigenvalues of f are having magnitude less than 1, this will converge to what we have seen. What did you see here? I minus A inverse, when all the eigenvalues were less than 1 in magnitude. So, this happens. So, this will converge to I minus F inverse. So, this quantity will be the balance amount. Now, I cannot throw it away, I can make it less by taking mu to be less. In fact, it is not so easy, because F itself depends on mu. You see there is a mu square here, there is a lambda is this mu square here. It is not, so this f itself consists of mu square, it is not that okay, you see mu square outside, mu square is inside also. But somehow I will find out this, I will expand this expression and see its dependence on mu and all that. So, by choosing mu appropriately, we can still keep it under check, but it is a constant quantity, we have to live with it, that is all. This much you have to live with, but at least it will not lead to instability, it will not lead to a situation where that error variance, each element of this vector is turning out to infinity. Okay. There is a stability issue. So, error variance is remaining bounded. That will happen only if the eigenvalues of this matrix F are kept within check, within their magnitude lies within 1 to minus 1, magnitude lies within 0 to 1. Okay. Now, for that I am not showing here, that definitely if you, then what you have to do, you have to take this matrix, study its property. This is the diagonal term consisting of rows, lambda into lambda transpose mu square. You have to see this matrix, study its properties, evaluate the eigenvalues, it is a bit clumsy expression things and all that, and then you impose the condition each eigenvalue magnitude less than 1. From there you will can generate a condition on mu, that what should be mu. Finally, everything will be boiled down in terms of mu. But it will be, you just hear me out, we can show that if you take that previous bound 2 by lambda max, or to be on the safe side 2 by tracer, that is a stronger bound, this is enough. This is sufficient to guarantee that eigenvalues of this matrix will remain bounded within 0 to 1 in magnitude. Okay. I am not showing that, if time permits, maybe some other day I will come back. I need to do some analysis myself, the books just mention this, I need to do some analysis myself. In terms of spectral radius, actually it will come. But our previous bound for convergence, that is good enough for this to happen. If you analyze this and all that, you can show, it can be shown that if you take lambda mu within this range, or rather mu greater than 0 less than 2 by tracer, that is a very stronger bound, 2 by tracer is less than 2 by lambda max. So, you are through, this will, this eigenvalues here will be bounded within 0 to 1 in magnitude, and therefore, this time dependent term will disappear, and therefore, we will get this. Okay. So, that is so this condition is sufficient for us, we can jolly well live, we can live very happily with this condition. Question is then, let us study this excess error, this quantity. Okay, why this quantity? We remember what was the excess mean square error? This much, epsilon square n was epsilon square mean plus this, and this you can write as lambda transpose k prime n, and therefore, I am interested here in epsilon square n as n tends to infinity. That time this quantity does not grow, but it attains some particular finite value, which is this side. Okay. So, I have to say see this quantity as n becomes infinity, that will be the excess mean square error, the minimum error, but this is the excess quantity, excess mean square error in the steady state. Steady state means n equal to infinity. So, I have to now study lambda transpose k prime infinity. Okay. Let us see this. What is epsilon square excess? Ex for excess, that was from this lambda transpose k prime n, and this is excess as infinity. Epsilon square excess, if you want I can put within bracket infinity, but I can drop that, I can just put that in the definition that epsilon square excess means steady state excess mean square error, that is this quantity as n tends to infinity. Okay. Now, what is this quantity then? Lambda transpose k prime infinity, and what is k prime infinity? This quantity with I minus f inverse, dot 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 infinity means it becomes I minus f inverse, right. Lambda transpose, so that means mu square, this lambda transpose here, and I minus f inverse, this I pi lambda. Very interesting, matrix, column vector, row into column, scalar, this quantity. Remember, f itself has mu square inside. Often we are interested in a quantity which is the ratio of this excess mean square error divided by, and this is called misadjustment. This is just a definition. So, you see this epsilon mean, this will cancel, this is equal to mu square lambda transpose. Okay. Now, how to analyze this quantity, how to analyze this? We will again invoke something which you can verify, but will not prove anything. That is, there is something called matrix inversion lemma. It is something, a very tool which is very commonly used in so many papers I find, so many books in communication, signal processing, control also. It says, let me write from the book, that suppose you have got some matrices, one square matrix A, suppose you have got a square matrix A say is n into n, is there in all books actually. It is called matrix inversion lemma. There is a matrix B, which is say M cross M, and there is a matrix C which is N cross M, I suppose, yes, N cross M. Okay, suppose 3 matrices are given. If you come across a term like this, A plus C B C transpose inverse, this kind of expression comes very often. C into B into C transpose. C is N cross M, N cross M, M cross M, M cross N. So, N cross N, N cross N, inverse is N cross N. Then this will be equal to some big expression, it will involve many inverses, and I am assuming the inverses exist. Under that assumption only the formula is valid, is not it? So, it will be equal to A inverse. This is sometimes difficult to remember, there is some carrying the book actually. Okay. I suggest you can verify if you multiply this by this quantity A plus C B C transpose, if you multiply this and simplify a lot of terms and some calculation, finally you will get identity matrix. This is how to build, but how this was derived I do not know. There may be something actually I do not know it. There will C B C transpose. C transpose A inverse C, yes, this is transpose. Okay. If you take this quantity, multiply either here pre or post and do all the term by term multiplication, you can simplify, I am sure you will finally get I matrix. So, that means this will be this into this will be I, means this is the inverse of this. This is a very well known matrix inversion lemma. Now, we have got this quantity I minus f inverse. Our problem is I minus f inverse. Now, what is f? By your definition of f, why did you do this f thing? F is this. F is this. For your benefit, I am writing what is f? F consists of that matrix, diagonal matrix P consists of the row values rho 0 rho 1 plus mu square lambda lambda transpose. Okay. Then what is I minus f? It will be I minus P, one diagonal matrix, minus mu square lambda lambda transpose. Nothing conceptual. This is diagonal matrix. What are the diagonal entries here? 1 minus lambda 0, 1 minus lambda 1, 1 minus lambda dot dot dot, minus and the square matrix. This together is I minus f. I can call this to be A, this A. I can take lambda to be my C, n cross 1, n cross 1. That is why lambda transpose becomes C transpose. Then what is B? B will be 1 cross 1. B you take to be minus mu square. Minus mu square is B. I can do that. Are you following me? I minus this diagonal matrix, very easy to handle. So, I am keeping that aside, I am giving A, the role of A to that. Inverting that is no problem. When A inverse comes so many times. Okay. Rest lambda, if I call C, n cross m means lambda is a scalar column vector, that means m is 1, B will be 1 cross 1, that is a scalar. So, minus mu square, this together is my scalar B, and C transpose lambda transpose. If you do that, put back in the formula, then what do you get? You get I minus f inverse is equal to A inverse, this with this definition of A, okay, A inverse, where A is this, okay, minus, I am following this for this result, minus A inverse Okay, before that you look at this quantity here, C transpose A inverse C. C is a column vector, A inverse is a square matrix. So, matrix into column vector, row into column scalar and scalar. So, this is a scalar, inverse means 1 by that, isn't it? So, it can be taken out of this entire product business. Whatever product matrix comes, A transpose C into C transpose A inverse C, C transpose A inverse, whatever comes that by the scalar number, that is all the elements of the product matrix to be divided by the scalar. Okay. That means and that is this quantity. I am just putting them back here. Okay, B inverse. B inverse means
The whole term how it is coming as scalar, B inverse plus C transpose.
aha, B is a scalar. So, B inverse is a scalar and this is a scalar, na, matrix column,
Okay, here for this, sorry.
isn't it? C transpose A inverse C. What is C? What is A inverse? A inverse consists of what? A consists of diagonal matrix. A is a diagonal matrix with diagonal elements 1 minus rho 0, 1 minus rho 1, 1 minus rho 2 dot dot dot. So, inverse that 1 by that. Okay. And then so, what you can do actually, you replace B inverse by, let me proceed this way, B inverse by 1 by minus mu square. Okay. Just a minute. It is a bit clumsy, so let me work out. So, 1 by mu square, so mu square will go up also, minus 1 by mu square, so mu square will go up also. Okay. Please check this calculation. I am doing extempore here. So, some signs and all I might just, some positive sign could be negative or negative should be positive, just correct me if I make any mistake. Mu square into this quantity C transpose A inverse C. C transpose A inverse C. C transpose A inverse C will be what? C transpose means lambda transpose. Lambda transpose diagonal matrix lambda. That means there will be a summation. Isn't it? There will be a summation. Or just a minute. Just give me a minute. Acha, I am just trying to check one thing here.
So, it will be lambda 0 square by 1 minus rho.
No, before I do at all those, Suppose I carry out this part, A inverse into B inverse. I am just trying to see something here. A inverse into B inverse plus A inverse into this quantity minus this quantity, the normal algebraic addition. I am just trying to see that something will cancel here. This is a possibility. This, what I am saying is I minus F inverse A inverse into B inverse plus A inverse C transpose A inverse C minus A inverse C transpose A inverse. These two quantities should be same according to me. A inverse C is a row vector, is a column vector, and this is a row vector. Okay, there is this a matrix? Because this is a scalar, there is some mistake somewhere.
Sir, I think that the lemma you have written, you have taken in a very complicated form. It has very simple form.
No, this is general term. A inverse C transpose A inverse. No, just a minute. This is turning out to be A inverse C transpose A inverse C, that is turning out to be scalar here, isn't it? But it is not scalar, because this is A inverse B inverse a matrix. This quantity, oh, yeah, what are you saying?
So, you have taken this lemma.
I am doing the most general lemma A B C.
Wait, sir, you have chosen the very complicated form. It has very simple form.
Very simple form. If you assume specific form for CBC, na CB, if you assume some very specific form, like if you take something to be identity and all that, these are I try to give you the most general result. This is the most general matrix inversion lemma.
So, basically, sir, we have used that lemma so many times, but
What is the form you are familiar with?
so we have B inverse equal to A inverse plus C transpose B inverse C. If you can
B inverse what?
B inverse is equal to A transpose A inverse, B inverse equal to A inverse plus C transpose D inverse C.
No, what is it that you,
No, if we can write this,
no, like here I have I minus, see you cannot just add some result, you have to consider, you have to restrict yourself to this thing, I minus P, a diagonal matrix minus this term. This is A, this is B, there you please say. Do not come with just some general result which you want to study somewhere here and there. This A, this B. I am trying to make use of the fact that this A is diagonal. So, A inverse can be easily computed. That is my goal from the beginning. I am just making some, making some silly mistake. It is because A inverse, B inverse is fine. That is a matrix. So, A inverse C transpose, A inverse C, that also should be a matrix, isn't it? Anyway, if it does not cancel, I cannot tell. I just proceed the way I was doing. Replace B by minus mu square. I just thought that some clever cancellation will take place. So, if it does not, no harm.
So, A inverse into C transpose we can't multiply, so we can take it as column vector.
Huh?
so that C transpose
So it will be
A
a-
inverse C is coming
It will be a
as
matrix.
Which one? Here.
I mean, A inverse and C transpose we can't plug it
A inverse and C transpose.
A inverse and C transpose you can club. Yeah.
because C transpose is a column. That is a row vector.
So you can first club A inverse C and then we can club C transpose and A inverse C. Then it will be a
Yeah. Okay. This is the problem.
you are not clubbing C transpose A inverse.
Anyway.
Club A inverse and C.
Anyway, I just thought of some clever cancellation. It was just my I mean kind of anticipation out. I thought something might cancel.
Sir,
Is something cancelling?
No, I mean, I have not completed, but it is coming as summation lambda I square by 1 minus rho I.
No, it's not. It's much more complicated than that.
No, no, that C transpose A inverse C is coming as that.
No, that's obvious. C transpose A is inverse, that's obvious. No? That 1 by 1 minus rho, that term will be below and lambda square will be on top and summation of that. That's too obvious. That's okay.
That's what you
I want to know. I thought that something might cancel and A inverse B inverse by, you know. Anyway, let me directly put because I know the result. Let me again write A inverse minus this is the result we had, right? This is a matrix C C transpose matrix matrix matrix. Okay. B was minus mu square. So, if you put that back here, you get it become plus or minus. One minus, isn't it? Into the summation thing. Acha, is A, our A is a symmetric matrix, isn't it? A is diagonal, but A is a symmetric matrix also. So, inverse of A also is symmetric, right? I am still, excuse me, I am still not able to give up the temptation here. I mean, whether I can play around with this. A inverse C, C transpose A inverse, because I can, there is very little left for the final result, and A inverse is same as A inverse transpose. So, this is matrix into I do not know, some cancellation has to take place on top. What I suggest is this, let me do from here for in the next class, okay. That will be better. But I will stick to this form. This I cannot, I do not know how you are suggesting to simplify it. This is the most widely used lemma.
This is the most widely used lemma,
हाँ.
but हो सकता है सर मुझे confusion हो रहा है.
And stick to this.
Yes, sir.
We have this form A minus mu square, this part.
Sir, A, B, C, these
हाँ, so A B C
general matrix.
हाँ,
More general matrix.
dual matrix.
हाँ. तो शायद इसका कुछ very simple form है उसको याद रखने.
No, that form will come by simplifying this. The form जो है, that will come. That is written in the book. I am not writing it.
Because sir, we have the proof
That
how that form is coming.
that you don't. That is not a big proof. You take this, multiply it, you will get identity.
No, sir, that is the reverse way proof.
हाँ,
Forward direction proof also we did.
अच्छा. Anyway, I will always start with this.
Oh yes, sir, that will be better.
I will always start. This is my start because even if I take the special case, you know, where this diagonal and this scalar and all that, it's better you know this proof. You know this inversion lemma. Okay, just a little bit is left of this. That's I mean, getting this matrix and all that, and finally a dependence on mu. Just two more lines are required actually, but I have to go through the derivation. So, I will do that in the next class. Okay. All right then.